The depth of water in Shepherd's Harbour exhibits simple harmonic motion about a mean level. The low tide depth of 4 meters is recorded at midnight, and the next high tide of 11 meters occurs at 6 a.m. We want to sketch the graph of the depth of water in Shepherd's Harbour over a complete 24-hour day. So we had 4 as the low at midnight, then 11 would be at 6 a.m. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3 and a half. The mean level would be around 7.5. So I'm just going to put that in like so. So it goes down 3.5 and up 3.5 from there. So simple harmonic motion, we know it's nice and symmetric. So the next low should be at 12. The next high would be at 1800. And then the next low would be at 24. And of course we know the shape is a sine graph. We could get some more points if we wanted to, but let's just try and get the basic shape, which isn't like that, because of course this was a minimum. So it would be going through here, then up and over, and then another 3, 1, 2, 3 for the mean point. So like so, then down to here, 1, 2, 3, we'll go through here, then maximum here, 1, 2, 3, over and down. A container ship named Violet requires a depth of 7 meters of water for safe entry into the harbour, for unloading at the dockside and for leaving again. Determine the times of the day correct to the nearest minute, between which it is safe for Violet to be in the harbour. We know the period of the motion is 12 because we had 2 complete oscillations in 24 hours. We also know that t is 2 pi over omega, and therefore omega is 2 pi over t. Omega would be 2 pi by 12, so omega is pi by 6. So if we consider the depth, first of all, the mean point was at 7.5. Then the amplitude was 3.5. And if we do this as a sine, we're going to have omega t, but we know it started at the minimum, so we'll do minus pi by 2. We're interested in when d is equal to 7. So let's go to the menu, graphs and table. Let's just clear anything that we have in there. And then we'll put in that y1 is 7. May as well put that one in first. And we also need to put in 7.5 plus 3.5 sine and then we need to put in the pi by 6, so pi divided by 6, let's call that variable x, take away pi divided by 2, we'll close the bracket there, and now we'll just plot that. We need a better view on that. So if we make the x minimum 0 and the maximum 24, the same it was on the other graph, and let's go from y is 0 to 12, then we should get the whole graph in. And the y1 is 7 is just here as well, and we want the points of intersection. So analysis, gsolve, intersect, and it's going to find this one first. So the first one here, let's just put the calculator so it's always on top, 2.726. Then we'll go across to the next one, 9.274. We'll go for the next one, 14.726. And the next one would be at 21.274. And it's when it's between these times and these times that it's safe. Now let's just go back to main. I'm just going to clear what's there. So if we have 0.726 and we multiply that by 60, that gives us 44 minutes to the nearest minute. So this would be at 0244, and then that will be to 09, and we'll do 0.274 times 60, and that's 16 to the nearest minute, so 0916, and then the other time would be 1444 up to 2116. We now want to know what percentage of the day the Violet can safely be in the harbour is. So if we work out the amount of time here, so that's going to be 9.274, take away 2.726, and then double that because it happens twice a day. And then what we want to do is this divided by 24 and multiply by 100, and that gives us 54.57%. Another ship, Elizabeth, requires a depth of at least d meters of water for safe operation. If Elizabeth can use the harbour for at least 80% of the day, determine the maximum possible value of d. So 80% of 24 hours is 0.8 times 24 gives us 19.2 hours. If we divide that by 2, that's 9.6 hours. That's how many times it's going to be able to be there each time. Returning to the graph from earlier, what this is telling us is that where we have this, that this is 9.6 hours. By symmetry, this is going to be 9.6 divided by 2, which is 4.8 hours. And the same here. This first maximum happens when the time is 6. So this one here is 4.8 less than that, so at 1.2. Now, to save any confusion, I'm just going to get rid of this first graph from here, and let's replot so we just have this one. And then we want a y calculation when x is 1.2, and that would give us 4.67. So it's going to be 4.67 meters.